In this training session, we will cover secure computation techniques, data provenance for secure computation, and provenance policies. Secure computation techniques are methods that use cryptography to securely compute functions when some or all of the inputs should remain secret to unauthorized parties. Some examples of secure computation techniques include multi-party computation, secure enclaves, and zero-knowledge proofs. As an example, consider a scenario in which Bob would like to compute the average of his, Alice, and Mallory's salaries. Alice and Mallory agree to participate only if they can keep their individual salaries secret. To do this, they can employ a secure computation technique that will only reveal the output of the average function to Bob while keeping each of their input salaries secret. They can each begin by encrypting their data with a secret cryptographic key. Then, Bob, Alice, and Mallory can each provide their secret inputs to the secure average function, which will cryptographically compute the average of their salaries and reveal the result to Bob. Now let's introduce data provenance for secure computation techniques. Data provenance is documentation describing the history of data from its inception to its latest state, and can be used to assess the integrity of data. It is represented as a labeled directed acyclic graph, and the possible nodes for a provenance graph of a secure computation in this study consist of entities, which can be a contract entity, a key entity, or a data entity. Agents can be an account agent or a node agent, and activities. The labeled edges can be one of 7 relations, which includes was attributed to, was derived from, used, acted on behalf of, was associated with, was informed by, and was generated by. Contract entities represent the logic that defines functions. Key entities represent cryptographic keys, and all other data is represented by data entities. Account agents represent users or organizations that own entities and share some responsibility for the execution of a secure computation. And node agents represent secure computation engines. Lastly, activities represent functions. Now let's discuss each of the provenance edge relations. The first relation is was attributed to. For this edge, the source node can be any entity and the destination node can be any agent. This relation means that the agent was responsible for the creation of the entity. In the following example, the data entity salary B is the source node and account agent Bob is the destination node. The relation between these two nodes indicate that salary B was attributed to Bob. The next relation is was derived from. For this edge, both the source and destination nodes must be entities. This relation means that the destination entity influenced the creation of the source entity. In the following example, the data entity average salary is the source node and data entity salary B is the destination node. The relation between these two nodes indicate that the average salary was derived from salary B. The next relation is used. For this edge, the source node is an activity and the destination node is an entity. This relation means that the activity used the entity as input. In the following example, the activity average is the source node and data entity salary B is the destination node. The relation between these two nodes indicate that average used salary B. The next relation is acted on behalf of. For this edge, the source node is a node agent, which is a secure computation engine, and the destination node is an account agent, which is a user. This relation means that the node agent performed a computation on behalf of the account agent. In the following example, the node agent SCE is the source node and account agent Bob is the destination node. The relation between these two nodes indicate that SCE acted on behalf of Bob. The next relation is was associated with. For this edge, the source node is an activity which represents a function and the destination node is a node agent which represents a secure computation engine. This relation means that the activity was executed by the node agent. In the following example, the activity average is the source node and the node agent SCE is the destination node. The relation between these two nodes indicate that average was associated with SCE. The next relation is was generated by. For this edge, the source node is an entity and the destination node is an activity. This relation means that the entity was produced as output by the activity. In the following example, the data entity average salary is the source node and the activity average is the destination node. The relation between these two nodes indicate that average salary was generated by average. The provenance nodes and relations can be combined to form provenance graphs. Let's walk through a partial provenance graph for the generation of average salary. This graph consists of 6 entities. Salary M, salary A, and salary B are all data entities. Average contract is a contract entity and represents a contract that provides instructions for how the average is to be computed. Key SCE is a key entity and represents a cryptographic key that secures the computation. And average salary is a data entity. This graph contains 4 agents. Mallory, Alice, and Bob are all account agents, and SCE, which represents a secure computation engine and is a node agent. And lastly, the graph contains 1 activity, which represents the average function. In this graph, salary M was attributed to Mallory, salary A was attributed to Alice, and salary B was attributed to Bob. Average contract in key SCE was attributed to SCE, and SCE acted on behalf of Bob. The average activity used salary M, salary A, salary B, average contract, and key SCE as input and was associated with SCE. The average salary was generated by the average activity and was derived from salary M, salary A, salary B, average contract, and key SCE. And lastly, the average salary was attributed to Bob and SCE, resulting in the final provenance graph. Now we will introduce provenance policies. Provenance policies are constraints placed on provenance graphs to either verify that data was generated as expected or to detect when data was manipulated in an unexpected way. Provenance policies are designed to prevent the consumption of untrusted data. Going back to our average salary example, Bob can verify that the average salary was generated as expected by specifying provenance policies that can be automatically checked when given the appropriate provenance graph. In this study, you will use 2 languages and systems to specify provenance policies that will be evaluated on provenance graphs. These languages and systems include ProProv and Rego.